way over here, but on this side, there's your leftover x. Now that's technically x to the 1, right? So before you move on, check that you didn't change the value. 144 perfect square is on the left. X to the 5th, not a perfect square, so x to the 4th times x to the 1, product rule, 4 plus 1 is 5. Didn't change the value, but you took the most possible stuff that you could perfect square, root and release, and the leftover bit stays on the right. Okay? So when you see one that involves anything that's not a perfect root, break it up into perfect root on the left and leftover bits on the right. Now, you're going to root and release the left, and that will be left over. So I'll write another long bar, and everything on the left is rootable. So I'm going to match my index of 2. So this is going to be something squared, and this is going to be x something squared, and then times that x, which is the leftover bit, which can't be broken up. So you don't use the power rule on the right because that's the leftover bits, nothing else to do with them except drag them along. Okay, so 144 is what squared? And x to the what squared is x to the 4th. So that right there gets rooted and released, yes, because we've got the 2's cancel out. Okay. What's in parentheses is your answer without the radical, root and release. You got the 12x squared. And this, by our product rule, this was still under one house, but by our product rule, we can divide into 2 houses. As soon as we've separated things, boom, there's our product rule. And the left-hand house got rooted and released, and the right-hand house was the leftover bits and stays trapped. Make sense? Okay. So let's break down some further variations. So I see that not everything's a perfect square. So first I'm going to break it into 2 things. Perfect squares on the left, dot, leftover bits on the right. Deal with the number first. Not a perfect square, so just like 98 wasn't a perfect square, we need to find a factor pair. If it's breakable, if there's nothing that breaks down, then it all would go on the right. 162 would go on the right. Okay? This is breakdownable, so we need to find the biggest possible factor pair. What you got? 81, yes. And that's another, this one also has, I believe, 9 is also? Yeah, 9 is also one. There might be even another. So there's other perfect square factors in this one, but you wanted the biggest one, so make sure your list is organized. You're reading down the right-hand side. And so we've got 81 here, and then I'll just leave some room for my x's and y's, put a dot, and put a 2 here. So I broke it down just like this, but I left room for my variables also. So the number is broken down, perfect square, leftover bit, still equals, I do 81 times 2, yes, check, it's 162, the value didn't change. Now we'll look at the x's. Is that a perfect square? What is the biggest perfect square it contains? Right, so x to the 6th and then 1 leftover bit. And I double check, x to the 6th times x, 6 plus 1, 7, check. Don't want to change the value. Y to the 20th, perfect square? So it all stays on the left. I don't have to break it up. So now, write the bar, I'm writing my index, and everything is going to match that index. Something 81 is something squared, x something squared, y something squared, and then times the leftover bit of 2x. And by my product rule, boom, I could just break it up into 2 houses, and that house is going to stay locked up. But the left-hand house, I can root and release once I unsquare everything. 81 unsquared. X to the 6th unsquared. It needs to equal 6, so what has to go here so it will? 3, because 3 times 2, 6. Reverse power rule. Just take that 6 and divide it by 2. Multiply it back to check. And y to the what squared? 10. Right, that's equals y to the 20th. Okay, so none of the value changed, but all of it was unsquareable. So the index and the exponents cancel out. And what do you write? What got rooted and released? Right. Now, did anyone accidentally, or at least their brain for a second, think they should write down a 3? If you did, that's fine, and if you didn't now, but you might later when you're working alone, it's just a little red flag. Some things are double squares. The square root of 81 is 9, but 9 is also a square. And sometimes when you're doing this method and everything, you think, oh, 9, your brain thinks perfect square, and you write down a 3.
But can we break it down?
No, you already have broken it down. Don't double break it down. Yeah, 81, you already unsquared. That's 9. Whatever's in parentheses when you cancel out your 2's, that is your answer. But sometimes your brain will think, oh, that's square root of 9 is 3, and write down a 3. But that's double unsquaring. That would be wrong. Huh? But I'm just warning you something that the brain sees, oh, 9, I want that to be a 3. But you already, as soon as you undo it here, you're done. That is your answer. That is your answer, x cubed. That's your answer, y to the 10th. And then times the leftover bit, which did not get released. It's locked up. Two more examples to finish it up, and just to let you know, the quotient rule we didn't get to like I did with my morning class. That's fine. That's where we'll start next time. Go as far as you can into the homework. Once you hit the quotients at the end, like the last fourth of the problems, then if you read ahead, and the end of the quotient rule is in the end of 11.3. Okay? So we'll pick up last time, but if you read ahead and try the quotient ones, even better. Okay? It's a similar type rule with 2 different directions. Okay? But we'll finish up with two examples of this with the cube root, and then we'll practice from there. So we already know this is not a perfect cube. That is. But if any part of it's not a perfect cube, then I'm going to have a leftover bit. I'm not going to be able to get rid of the radical entirely. But I want to pull out, root and release what I can. So first write it as a long cube root. And 24, perfect cube? No. Does it have a perfect cube factor?
Yes.
Yeah. That's pretty small, so really it's only, 27 doesn't even count. It's either 8 or 1. Well, 1 doesn't matter. So it's either 8 or nothing, right? Yeah. So 8 is a perfect cube. 8, and we'll leave some room for the x and y, and so times 3. Yeah. So the perfect cubes are 1, doesn't matter about 1 because it doesn't change anything. 8, yeah, 27, too big. Okay. And you can certainly make your factor list on the paper on calculator, and you'll see that. But with cubes, there's not many to go through, especially when you have smaller numbers here. Okay, x, perfect cube?
Yes.
Yeah. So this, if it's divisible by 3, if it's divisible by the index, you can make groups of 3, then you're good. It's perfect cube. What about y to the 9th?
Yes.
Yeah. Both of the variables are perfect cubes. So cube root, something, 8 is something cubed, x, something cubed, and y, something cubed. And then times, the 3 is the leftover bit, and by the product rule, I can just divide up the houses, boom, that's going to be its own house, and it's not going to be released. But we can root and release all these. 8 cube rooted is 2. X to the 6th cube rooted is 2, because 2 times 3 is 6. Reverse and check. Y what times 3 is 9. 3 times 3 is 9. Reverse the power rule. And then 1, 2, 3. That's what you root and release. Because the 3, those exponents and index canceled out, killed the radical, and you're left with 2, x squared, y cubed, and then this part, which is still trapped. The leftover bit stays under the radical. One other example to show one other principle of the cube root to be careful about, and that will take us perfectly to time. Any questions with this? Okay, so try this one. It's blank on the back, so you can just go ahead and one last product rule example here. Write 3 cube root of negative 125 x to the 5th y cubed z to the 22. First, scan over. You've got 4 things here, a number and 3 variables. Scan over them. If any one of them is not a perfect cube, then you know you're going to have a leftover bit. So if any one of these is not a perfect cube, then your first step is to put perfect cubes on the left and leftover bits on the right. You don't need to reverse power rule yet. Just break up into perfect cubes and leftover bits. If everything here was a perfect cube, then you would just go ahead and use your reverse power rule, because you know everything would be rooted and released, no more radical. because you know at least one thing here isn't, then you need to do an in-between step of breaking it up into perfect cubes and leftover bits. Okay. So, negative 125.
5 cubed.
Right. So that's just, that is a perfect cube, so I'll just keep it on the left. I don't have to break it up into parts. X to the 5th, is that a perfect cube? No, because 5 is not a multiple of 3. What's the biggest group of 3? X cubed, right. So, let me put a dot here. So if I have x cubed is the biggest group of 3 because another group of 3 would be x to the 6th. That's too big. So if I use x cubed, what's my leftover bit? Right. So, and I do a quick check. 3 plus 2 is 5. Good, didn't change the value. And this must be less than 3. If it's 3 or greater, then you could have taken out another group. Okay? So if you've got a cube root here, your leftover bits will all be squares and singletons. Okay? So, y, perfect cube or not? Yeah, it's a multiple of 3. The whole thing can go here, there's no leftover bits. Z to the 22, perfect cube? No. What's the biggest perfect cube, the biggest multiple of 3 less than 22? 21, yeah. 21, you're looking for a multiple of 3. If 22 is not a multiple of 3, you're looking for the biggest multiple of 3 that's less than that. 22 is not a multiple of 3, so you say 21. Oh, yeah, that's 1. And then that means what's leftover bit do you have? Just Z to the 1. Yeah, there. 21 plus 1, 22. Didn't change the value. Of course, these are both less than 3. They're the leftover bits. I did the biggest groups of 3 that I could get out of them on the left. Now, you reverse power rule. You're going to have 4 houses here for the number cubed, x to the something cubed, y to the something cubed, and z to the something cubed. 4 houses. All 4 houses will be able to be rooted and released because they're all perfect cubes. Times our leftover bit, x squared z. And by our product rule, we can go ahead and boom, that leftover bit is going to have its own house. It's locked up. And we just have to root and release the left-hand side. Negative 125, cube rooted. Negative 5, right? What would make this true? X to the what cubed?
Just 1.
Uh-huh.
So it's just like
Yeah. And y to the what cubed? Yeah. And z to the what cubed?
7.
That's where the 7 comes in here. Just double check. Okay, that's negative 125. That's x cubed, y cubed, z 21. Check. Okay. And 1, 2, 3, 4. All root and releasable because I made them that way. I moved everything that I could root and release to the left. Negative, and I write just what I see in parentheses. Negative 5, x, y, z to the 7th. Now definitely here with an exponent here and an index of 3, really want to put that dot there to be really clear. Don't forget your index of 3 here, because even when you did the product rule here, you didn't, you could write in the little 3 if you want, just to remind yourself. The leftover bit is cube root of x squared z.
But the cube root, didn't that cancel whenever you did the third step?
Here?
Yes, ma'am.
No, because if this is a cube root, by the product rule, if I've got a cube root of something, if I break it into 2 houses, they both still have the same index. This isn't going to magically change into that's going to stay a cube and that'll change into a square root. No, it's cube root of the rootable bit and cube root of the leftover bit. And cube root of the rootable bit got rooted and released. But it's also then, by the product rule, the cube root of the leftover bit, which didn't get rooted and released, so it's still the cube root. And surprisingly, I'm usually like 2 or 3 minutes later with you guys than my earlier class, but this time 2 or 3 minutes earlier. Yes?
On the previous problem,
Uh-huh.
why didn't we do that to the 3?
Thank you. Good catch. That's exactly what we're saying here. Yes. Very good catch. So, and I would want to use the dot too, because this is 2x squared y cubed, 2x squared y cubed, but then a dot, because I really want to make sure, don't forget, there is a 3 there. Cube root of 3, not square root, cube root of 3 is the leftover bit.
But
Yes.
what optional you have
It's not optional, no. If the index is 3, the product rule says your two houses that you break it up into have to have the same index. Just like you can't combine them with multiplication unless they have the same index. Yeah. Now you don't have to have that dot, but you can see how it makes it a lot clearer, exponent versus index. Not a problem typing in my math lab boxes, but do it in your notes, and for me on the exams, I'm real clear what goes where. All right, I will be in the lab in about 10 minutes. Again, remember about the sign-in for an office visit, and if one of these don't work for you, just let me know, and I'll see what we can work out.
The top part.